storage, but please keep in mind that pretty much all what we're talking right now is applicable for the other frameworks other than Spark, such as, I don't know, Hive, Presto, Dask. So pretty much every large-scale computational network. So this slide is the slide from the project series itself. Dr. Lake gave an introduction to this slide. And this is to give you kind of the overall view of where the near data processing fits in the picture. So the basic idea of the NDP is if we can extract certain operations from the plan during the process of query optimization. Usually the distributed clusters, they run through the process of the query optimization. Again, it's just a typical relational algebra processing. And if at that time we can extract certain filtering, certain projections, or certain aggregate operations, which has a key component to it, is they are reducing the data which will be needed as a result. And if we can push it down to the storage and perform near data processing, we can save pretty significantly on the data transfer and network bandwidth, and therefore improve the performance of the whole cluster. Okay, so before we starting to talk about our solution, it's important to understand that there are many types of the storage. Right now I listed 3, but you can probably imagine any other configuration of the storage. But the typical ones is a traditional storage appliance. You just buy an equipment, and you can think of it as a box. It has some limited connectivity, so it may only have that much of connection ports, physical ports, and it has a limited computational capabilities because this box has only that many CPUs. Another storage type is the cloud storage. Cloud storage has another property. It typically has very limited bandwidth because the input and output is going over the Ethernet. And however, it has, again, virtually unlimited computational resources because the back end of the cloud can be very big. And the last one, it's a distributed storage, which consists of many nodes, and add more nodes. It tends to have more scalable bandwidth. It tends to have better scalability within the bandwidth, and it tends to have computational resources, because if you out of computational resources, you can potentially buy yet another storage node. Now, we hope that what we will talk about today, our solution, will benefit all types of these storages, but in slightly different areas. Our main focus is the traditional storage appliance, and maybe with a bit of the cloud storage, but that's what we are aiming for. Okay, so network is one of the performance bottlenecks. It's important to keep in mind it's only one of the bottlenecks. It may be many others. For example, the retrieval of the data from drives or anything like that. However, what we're focusing in that effort is the network bandwidth and a little bit of the computational resources of the cluster itself. Now, in some workloads, network bandwidth is really a major bottleneck. TPCH benchmarking can clearly demonstrate it. And again, TPCH is well known in the industry, a lot of papers written about it, and it's very easy to measure and justify various tests and parts of TPCH. And in a very simplistic setup, the single core of a Spark worker can easily digest Parquet data at 60 megabytes per second. It's reasonably fast. The decompression rate of Parquet is fairly fast, which effectively means that just 32 worker cores, and you can think about it as just 4 physical nodes, can fully saturate 10 gig network. Network in it can be a switch, it can be a storage 10 gig connection. You can always argue that storage may have 3, 4, 8 connections to the total of 80 gig. Yes, but we need to scale with the physical nodes as well. So for physical node, it's not a big cluster. Now, storage side near data processing. So the main idea is to use the storage capability to perform some data operations to reduce the network traffic. And this kind of the sole reason of what we're proposing here. Some operations, again, projections, it limits the number of calls. Filtering can significantly reduce the amount of output data. Aggregates, if especially with the group by, they also can very significantly reduce the amount of data. However, group by operation may be expensive. It depends on how the data is laid out. Now, read-ahead, prefetch techniques, and NDP. So what that is, we talked about the planning phase of the planning phase, which usually performed by the cluster. It is a phase when you take the user query and run it through some sort of the optimization algorithm. In that optimization algorithm, you try, in a typical database case, you try to optimize indexing and so forth. And you also try to figure out how to distribute that work across your cluster. Now, if at that stage you will let storage know what you are about to do as a cluster, the storage can proactively perform certain operations. And when you, at the time when you will actually need the data will be available. So you can think of it as some sort of the opposite of the lazy loading approach. So if I will know that I will need the data in the future, and I do know it at the planning stage, I can ask storage to make this data available for me. Another benefit of the NDP is storage may have a special purpose hardware, some powerful GPUs or even ASICs, which can be installed on the storage nodes and can be used to improve the performance, because we can literally DMA from the NVMe drive directly into the GPU. But installing such an expensive hardware on every compute node maybe just expensive. It's that approach. We may like to have each compute node to have the latest version of NVIDIA GPU, but it may be not practical from the price point of view. Okay, so what we're proposing? We're proposing, again, we're focusing on Spark, but please keep in mind that it can be applicable for pretty much any other cluster framework. We're proposing an extension to the Spark. Spark has a native way to load certain extensions into various stages of its own processing. So we call it the rule-based engine after the Spark approach to the logical plan optimization, which is optimizing the logical plan on a rule basis by traversing the DAG and performing modification of the DAGs to make it really more optimal. So why we chose this approach? Because Spark has a native pushdown capabilities, and they are vastly designed to work with the SQL servers. And part of the push downs are actually going directly into the data source, and the, let's say, filtering, it's performed at the worker level. So the majority of the Spark data source V2 push downs, they still bring the whole data from the storage, but the processing, the filtering is actually done at the worker level. And as well, it has certain limitations because at the time when Spark optimizes the logical plan, it doesn't really know what storage is capable of. Okay, so this part of, let's say, some sort of the handshake with storage and understanding what storage can and cannot do and with what speed is currently lacking. So what we do, we just inject the rule into the Spark optimizer. It's a standard way. So the Spark code is not modified at all. The Spark code is just instructed to load yet another rule from a jar file. That rule, that our engine will recognize a set of operations which can be performed on a storage and which can potentially reduce the output, the data size, which is which storage will have to send back. So once logical plan is optimized, the logical plan is instructed to use an NDP data source, which is playing by all Spark data source rules, and which internally uses an NDP client, which is just a communication mechanism to the NDP server, which is storage. Okay. In a cluster setup, that will look something like that. So you do have a Spark driver, and the Spark core, it's loading automatically the NDP rule engine. The plan gets modified, NDP data source get engaged, and we can, on the left communication line, we can talk to the storage and ask some capabilities. For example, we can ask storage if group by operation can be performed fast enough, if we have a memory for that particular group by operation, and how busy the storage is. I give you the example: if storage are currently in a rebuild mode, it's probably not the best idea to use its computational resources to perform some cluster operations. So once that information is established, Spark will distribute the tasks for their workers. We have here an example of the 4 worker nodes. And the task itself will use a standard Spark mechanism to talk to the NDP data source, which plays by all Spark rules. And internally, it will use NDP client and communicate with the storage. Okay, so this is that's a picture of how that looks like. Please note that there is an NCP. There is an NCP box, which is the last stage of IO flow, and this box is designed to deal with the fact if storage is overwhelmed or for whatever other reason is not capable of performing the push down operation. Plan is already modified. Spark is inflexible. Spark in that area. Spark already has modified plan, and everything, all the data which is flowing inside the cluster has to be with, has to comply with existing schema in that plan. So we cannot just say, hey, we are not going to process the data in the storage. We have to provide a solution when if storage is either either saturated from the computational point of view or have some other problems, we still need an entity to process the data in an old way. in order to provide to the Spark the data which it expects. Okay, so NCP, it stands for the near compute processor, which will mimic what the storage would do if he will be in a good health. Okay, that's just a picture of our small cluster. Just to help you to visualize how we distribute the data. So we have 4 physical worker nodes, we have a driver node, and we have a storage box which has the network connectivity. It's a 10 gig network here. So that's just to make sure that we don't have the bottlenecks in that area. We are working with the Parquet files. And we using the database, PCH database of 100 gig. We have tests with the 400 gigs, so to make sure that it is scaling. But for the sake of this presentation, we believe that the 100 gig would be enough. Okay, and that's what we found. We have 22 TPCH tests. And this graph, it's measured by how many percent we improve the time which it takes to the cluster to perform the test compared to a native Spark way to perform that test. The interesting notes here. First of all, the average improvement, if we're looking at all 22 TPCH tests, it's a little bit above 30%, which again, in our mind, it's not a small improvement. Another interesting point that not all the tests actually benefit from it. We can look at the test 2 and test 5, and there is no improvement. For the test 2, for example, they have a complex UDF in front of the filter, and therefore we cannot push it down because the Spark UDFs are organized in such a way that right now it's a little bit difficult to push them down. And for example, the Q1, the test number 1, it does have the filter, and this filter is pushed down, but it doesn't filter much data. It brings back almost 90% of the data back. Therefore, we don't have big improvement. However, tests like 14 and 15, they do have large projections, so they bring back some small amount of columns, and they do have a heavy filter over those columns. So, and the data reduction is significant. To show how that looks like, it's the same set of tests, but what we're charting here, we're charting the reduction of the bytes which we have to transfer over the network while we're performing the tests. And we comparing it with the bytes which Spark transfers to perform the same test. And you can see, as I said, that the test number 1, it doesn't really have big improvement, as opposed to, let's say, tests 14 and 15, which do have big improvements. Now, and overall, we're sending over the network of the cluster 60% less data. That's for the data transfer part. And the last one is, it's a bit counterintuitive because users typically care about how fast their tasks run, but this, we believe it's also important metric. This is metrics of utilization of the CPU of the compute nodes. What does it mean? It means that when Spark runs in its native way, it needs on average 40-something% more, it consumes more CPU load on its node by some 40%. And effectively, it doesn't provide time benefit immediately, but it gives a cluster as the whole an opportunity to run other tasks in parallel with what we are doing right here. And those resources are kind of free, okay? So that's, again, we believe that this is an important metric. Okay, now the problems. The biggest one is that the storage appliance computational limitations. Again, storage has only finite number of the CPUs, memory, and so forth. And the large amount of compute nodes can just saturate that resources. Yes, storage can do the data reduction, but it needs to open a file, it needs to decompress it, it needs to run some filtering operations. Filtering is reasonably cheap, but if it's aggregate or group by, it's compute intense operation. And it cannot always keep up with the scale of the computational cluster. So what we proposed, what we actually did, we figured out a way to dynamically determine how busy the storage is, and upon a request from the cluster, we make a dynamic decision if we want to process that data at the storage level, or we want to delegate it into this. You remember that it was near compute processing box. We just delegate it there. We don't have improvements on the bandwidth, but because it's really performed the same way as the Red Bull Spark would be, but we do not saturate the storage, and for whatever load storage can take, it will reduce the bandwidth. And the next graph will show you how that looks like. So black line, it's a Spark. Okay, and on the left, on the y-axis, you can see how much time it takes to perform a query. Okay, so the 300 at the very top line, it means that for the Spark cluster, purely Spark, within the 4 cores, 4 nodes, 1 core on each one, it will take Spark 300 seconds to perform TPCH query 14. Okay. Once you start to use NTP on the same node, on the same cluster, same 4 cores, same everything, you will see that the blue line, which will take 109 seconds to perform exactly the same thing. It's almost 3 times faster. However, if we are starting to scale the Spark cluster by adding more nodes or more computational resources, what we will figure out that NDP itself, the near data processing itself, doesn't really scale, because we have only single storage appliance or only finite number of the resources. And once we stop scaling at whatever 12 cores, our performance would be worse than the performance of the Spark. So if we are going to engage NCP, near compute processing capabilities, somewhere in between 8 and 12 cores, this is the green line below, we will kind of benefit from the both worlds. On one hand, we will not saturate the network because we do reduce some amount of data by storage. And on the other hand, we will not saturate the storage processing or compute capacity. And that the green line is, it's kind of attempt to find the best middle ground in between 2 worlds. And again, results, we believe that's pretty impressive. The next one is, we talk a bit about the scheduling limitation. NDP can reduce the data as we talked about it, but it still needs some time to process the data, right? So today, Spark, when it creates a logical plan, it distributes it to the tasks, and those tasks are not aware of any of the timing limitations. So the task is submitted to the worker, and it just waits for the storage to bring the data. And it's not a big problem, but it can be optimized further, because if tasks scheduling will be a bit more intelligent, that core on which task is just sitting and waiting can be utilized by Spark for doing something else. Okay. Now this one, and that's important thing, is that the reducing the CPU utilization, it actually can help other workloads to use those CPUs when they are running in parallel with that particular query. That freed CPU capacity can be used for other workloads to run in parallel. And even if NDP itself doesn't show big improvements in a time to process a particular query, just a reduction of CPU consumption will help the other tests which are running in parallel. To demonstrate it, we created a special monitoring tool. It's a simplistic one, when we just monitor what is the CPU, monitor and record the CPU utilization and the network bandwidth on a cluster nodes while we're processing the queries. So, and that's how it looks like. So if we're focusing on this Q14, this is a simple Spark execution of the Q14. We do have some CPU load, and we do have a network bandwidth. Rx is what the node receives from the storage. We have 1 gig network on the storage node, and we can pretty easily see that in that particular case, the network bandwidth is saturated at about 120 megabytes per second, which means it's 1 gig connection. We saturated, there is nothing we can do about it. This is the Spark. However, Q14, as I told you before, it does have some heavy filtering. And that heavy filtering reduces the data which is output by storage by manifold. And if we're running the same query in the same setup by using NTP processing, we don't consume CPU. At the end, you have this hill at the end with both CPU and the network. This is when the task is reporting the information back to the Spark driver. So it's inevitable, it has nothing to do with the storage. And the first blip is when this particular worker node actually receives all necessary configurations from the Spark driver. But in the middle, the Spark node doesn't do much. And the question is, that's why we're showing those graphs, is how we can utilize that time to do something else, and if it is feasible. And okay, this graph is another query. We chose that test Q2 because it's not capable of doing NTP, because the internal structure of the test doesn't allow the push down. Okay, that's how it looks in Spark, and there is nothing NTP can help here. NTP just not in play in that case. But if we will combine those two tests together, we can see some interesting results. So this graph shows how the Q2 and Q14 run together on the pure Spark configuration. And you can see that it takes 250 seconds to run them both together. You can see that there is some reasonably, it's not very high CPU consumption. And the reason behind it, it's not very high, because our network is saturated. If you will look at it, network on both receive and transmit side is pretty saturated all the way. And And that's what the limitation of the Spark in that area. And that's why the CPU is not very high, because all what CPUs are doing, they are waiting for the network. And now in that graph, we will combine the two, but with NDP. So Q2 will not change because nothing cannot be pushed down, but Q14 does some significant push down. And as a result, what you can see is that there is some CPU changes in that area. CPU is less jittery, let's put it this way. The overall two tests run in just 175 seconds instead of 250, which is not a small improvement. And you can see that in the first 75 seconds of combined run, the network is not fully saturated, because the first 75 seconds, it's where the Q14 running in parallel with the Q2. And Q14 doesn't need network and doesn't need CPU. So all those resources of the cluster are available for the Q2 test, which is running in parallel. And that's would conclude our presentation. There are, at the last slide, there are some Git repositories, materials, and whatever you can. We hope you find useful. That's it, and thank you.
All right, thank you, Peter. Do we have any questions? So let's open this up for discussions. Do we have any questions? So I see Peter raised his hand.
Yes.
Go ahead, Peter.
So I'm curious. So you were showing that, you know, in a sense, rather than you know, that you had, rather than basically getting more higher utilization on the compute nodes because you were feeding them data quicker, you were getting lower utilization because there was, you know, more processing because you were substituting processing outside of them. I'm curious about what the overall effect was. In other words, is this something that was actually reducing the total amount of computation because of where it's being performed? Because I worry a lot about sort of, you know, provisioning resources on the storage nodes runs a significant risk of stranding them for some workloads, as opposed to, you know, allocating them with the compute nodes. So if it's merely moving it from one place to another, that, you know, that's concerning, as opposed to, you know, an architecture which actually does the work more efficiently.
Okay, so first of all, I agree with you. There is a big concern of saturation of the storage. And the thing is that what we need to keep in mind, what I would suggest to keep in mind, that the transferring the data is expensive operation in and of itself. And what we found out that for example, the filter operation, simply comparison a floating number with another floating number, which is fully parallelizable and effectively very fast with all vectorization based on CPU and you name it, it's probably an order of magnitude less expensive than the data transfer itself. That's what we found. And that's one thing. And another thing, it's important to keep in mind, at least in a Spark case, that Spark Worker is the Java application, which has all its, so it does have some good parts of it, but it also has some performance implications. Well, I'm trying to be careful here, not to offend anybody. But the thing is, we performing near data processing by native machine code. It's compiled C++ code. It's optimized or potentially optimized all the way till tomorrow with OMP, with vectorization. And again, I mentioned GPU. I can dump a vector to the GPU and ask him what indices of that vector is greater than 300. So we do expect that kind of optimization. That's one thing. Another thing is, once we are sitting on the storage, we can presume, or in some cases, the data is already in the cache. My data is in the cache. I can run per se a query from the cache of a storage natively. I literally, it's memory mapping and it's a memory touch. Okay, as opposed to get this data off the wire or get this data off the cache, package it in a certain way, transmit it back to the Java application using some whatever Spark does, GNI, to open it, to parse it, and only then they come to the point when they can compare it. So, yeah, but again, it's still some 20 or 30 computational nodes. Even with Java, they can easily saturate the storage. And for that reason, we provide some fallback mechanism, let's call it. Okay.
So I want to add to what Peter just said, right? I want to make 2 points. The first point is that what are we trying to achieve here, right? So obviously, we will be able to reduce the resource utilization on the compute side. So that will allow the compute cluster to take on more workload, right? That's one part. Another part is that each individual application, right, on the compute side also can benefit, right? Because the latency for each application is significantly reduced, right? So that's my first point, what we're trying to achieve. The second point I want to make is that Peter was concerned that what about the resource provisioning on the storage side? Basically, are we trying to just move some of the computing power from the compute cluster to the storage cluster? So that's not the idea here. I was talking to someone at Amazon just last week. They told me they have a project called Aqua. Basically, Aqua deploys specialized purpose-built hardware accelerator on the storage side so that they can do a lot of processing on the storage side to scale the compute side better. So that's what they do. They do use specialized hardware. But what we do is very different. Our assumption is that the storage servers already have some computation power, no matter how limited it is. They come with some computation power. We just want to use that to the extent possible, but we're not going to add any additional hardware. So whatever computing power we can harvest from the existing storage servers, we're going to use them. And then if we are saturating the storage side, we'll stop that processing. We're not going to just do all the processing. We'll do some throttling, right? So when the storage servers are busy, then we stop. So we're not trying to overload the storage server, right? So that's a fundamental difference between what we do and other projects like Aqua do, right?
So, could Aram, mind if I just follow a slight bit on this? That it seems then that yes, you basically have a more efficient way of doing things, which, because it's not general in the way Spark is, you can't just substitute everything, but it actually does do that part of the work more efficiently. What's interesting to me is it does seem like that's also disaggregatable in the sense that you could have storage nodes that were merely were enough to pull the data off and pump it over an Ethernet, which is with the right code is about as efficient as reading it off an SSD. and then disaggregate your near storage processing into a layer on top of that, and then talk to Spark, and in fact, basically construct that layer out of the, out of some fraction of the CPU that you saved on the Spark side, and you probably would still be ahead as well. That to some of the gains there are because of coming up with this more efficient, although less general, mechanism that you've inserted underneath Spark.
Yeah, can I jump in there? Because I think Peter and I were sort of on the same page. I really like what you're doing here, and there's sort of 4 different aspects of that you've talked about. Is the data cached? Sorry, can you guys hear me now? Because I know you couldn't.
Yes, we do.
So one of them is the more efficient computation for restricted API. The other one is the high bandwidth to the storage. The other one is, Peter, you kind of alluded to the fact, Peter, the future way, Peter, is alluded to the fact that data would be cached or likely to be cached. And I think that if you kind of take that all into the, you can imagine arbitrarily sort of allocating, I can imagine there being much higher bandwidth for certain physical infrastructure near to the storage. And as Peter says, disaggregating, so having that general concept of disaggregating the compute from the storage, tying together, for example, the caching layer or a caching layer to say, what data are we actually caching? And I could see a lot of sort of really neat potential to not just sort of embed this with one set of trade-offs, but generalize this to allocate compute near storage, and in a multi-tenant environment with a lot of different sort of demands on it. Sort of where do I want to buy that compute, and how can I get compute near it, and what's the trade-off on where I'm doing my compute if I do have those resources that I can allocate nearer to that storage. Does that make sense? So I kind of think that what you did is really cool, but it sort of doesn't exactly apply to the assumptions we make, but it seems like it could be generalized to apply to the assumptions we're making.
That's a very good point. Let me comment, and I think Peter can follow up. So that's a very good point. So our vision is that, these days, I like to talk about the memory hierarchy, right? Meaning on the compute server side, right? You have the CPU. You have the main memory. You have the storage class memory. You have SSD and HDD, and then hierarchy. On the storage side, you have the same memory hierarchy, right? The two sides actually come together and form an even deeper hierarchy. And then the current state of the art is that for every layer of the memory hierarchy, there is some compute power. So that processing power exists on every layer. So we should not just think about the compute server is the only place where computation can take place, right? So there's computation can take place at anywhere across that hierarchy. Obviously, different layers will have different capacity. So it's a matter of how we do that better scheduling to place the computation task at the right level. So I think that itself is a very interesting research problem. Peter, do you want to add anything?
Okay. Let me put it this way. Yes, we can try to generalize certain things, and yes, we. How would I say it? This is the thing. We all if we try to distill what we kind of try to achieve, we're trying to make a query planning, aware of the capabilities of the hardware, if you think about it that way. Because it's that intelligence which knows that the entities which is holding the data is capable of processing it and capable of a particular set of operations. So I'm not sure that I just don't know, it's a part of the research, that it would be efficient or optimal to try to generalize it. But there are if there are a set of unique operations which can be performed very fast and provide any benefits for the reduction of the traffic, it may be interesting to make the planning aware of that fact. Now, why I'm always focusing on the traffic? Because otherwise you can provide the same computation just by simply scaling the cluster. Okay, it will be not interesting to provide some fast compute, whatever it is, because you can always substitute it by the number of the computational nodes. That's just my take on it.
So one more point I want to make is that I think Oran also talk about caching and so forth. So obviously we have some caching mechanism in the context of NDP, right? So that we can access the data more efficiently. Actually, we have another large body of work related to caching that's in parallel to this near data processing work. For that one, we actually first we don't just use cache on storage side or compute side. Actually, it's a multi-tier cache. So certain data is stored on the compute side, certain data is stored on the storage side. That's one thing. And secondly, we try to cache the different kinds of data, not just the raw content from the storage server, also some metadata that will help us decide whether certain partitions can be skipped or not, right? And also we try to rearrange certain data so that you can make the access more efficiently. So we do have another body of work related to caching. We can talk about that at future time. Any other comments, questions? So maybe I can turn the table around and ask Shisha and Oran the question. So do you think this kind of NDP work can be possibly integrated with what you guys have been doing, right, in terms of prefetching and caching?
So I think that, so if you think about the relationship is that on the one side, we've been talking about sort of this distributed cache near compute clusters, right? So clearly one could imagine in that environment having accelerators there or in fact doing exactly this optimization that you're talking about of this optimized code executing there in this distributed fashion, because kind of our assumption is that the data lake resources from a caching perspective have to scale with the data center that's accessing those resources. So on the one side, that makes sense. And totally on the other side, when we're thinking about, we're sort of starting to play with hybrid cloud storage and a more distributed thing, if you take sort of the ESI stuff that's moving along in Open Infra Foundation, you sort of say, well, could you allocate sort of physical resources where you need them? Because that's where the bandwidth is available, and doing certain computations there. So I think it's super interesting. I think there's a ton of potential ways of overlapping this, of integrating these ideas. Peter, are you in the same?
Yes, I mean, I think that maybe another way, that this fits in very well with a caching strategy. I mean, I guess, what I see with some of the big, like the big storage system they have out at the Holyoke data center, that at a certain point, putting resources onto the compute nodes, adds a significant constant factor to, the per terabyte cost of storage, especially nowadays when, there's such a huge difference between, the cost of the number of cores you put in a compute node and what you need to put in a storage node, in a bulk storage node, for instance, for disk, where, caching, a caching layer is essentially, a computational support layer. It expands with the amount of resources you dedicate for compute. It's funded out of the resources you provide for compute, and techniques like this, are, would really, naturally live in that layer. And, and now, and, and sort of my initial worry, like I was saying, was, oh, it's just shuffling computation. It's not. It's providing, a more efficient way of doing the computation. And, was able to get away with that because
stating this a slightly different way, is that in our model, we have a really, really slow data lake that's using high capacity drives, potentially SMR, whatever, that's located in one place in the data center, right? And shipping computation near to that isn't worth it because it's really slow, right? And we're overcoming that by having caching that's distributed, given the sort of same assumption of limited network bandwidth, right? So I think what your assumption that you're making is that you've got efficient storage and you've got a cache integrated into the data lake. And in that scenario, what you're doing makes a ton of sense. But I think what you're doing also makes sense in our scenario, where the data lake is assumed to be slow, high capacity, but you're caching things near to where it's being accessed. And that's where near data processing will give you a huge advantage.
Right.
Yes, I understand where you come from. So your assumption is interesting because when I look at the currently available commercial storage products, they all come with very efficient CPUs, very, very high capacity CPUs. So I think that's something we can reconsider, right?
But when we built it of commodity for Nessie, like it doesn't. It actually comes with.
When you start looking, but those, I guess the question I have is, are those SSD based or disk based storage systems?
Okay.
Because for SSD based, yes, for the sheer PCIe throughput you need for more than a couple of NVMe drives, yes, you need a fast CPU. You're amortizing the cost over a fairly a bunch of expensive devices that are plugged into that. Once you get to capacity storage, that's the disks haven't been getting faster for a long time, and while the compute CPUs are getting faster, we put a few more of them into a box each year, so it's up to like 60, or we're not using 60 in Nessie, but the number of disks in a device is quite high, and you're sort of trying your best to keep the cost per spindle of the sheet metal and everything else low.
Yeah, the cache is sort of irrelevant there.
Yeah, and yes, and you're not doing in a scale-out system with thousands of disks. Caching at the individual storage nodes isn't effective for most things, so the cache really needs to be at the other end of the, somewhere on the other end of the wire after you've picked out, the disjoint set of data from a bunch of disks that's relevant to what you're doing.
Yeah, so this isn't just, at least from my perspective, this isn't sort of a criticism at all. This is more saying that I think what you've done is more generalizable and applies to this radically different design.
We're trying to figure out how to put it, and there's this natural place that it actually sits right next to a lot of the work that we've been doing, even though ours isn't fully on the back end of the storage.
But let me ask you the following question. And so, for example, when you say that you have some sort of a centralized cache, which lives a little bit outside of the slow storage, right?
Mm-hmm.
So in that cache, right now, today, you actually holding the data, right?
Yes.
And in order for it to be retrieved faster later on. And I can argue that the less data you have to hold, the better utilization of the cache you have. Oh, not exactly. So that's that. So effectively, what I'm trying to say is, if you translate at the planning time, if you will be able to reduce the amount of data which you will be interested to retrieve later on, that may have to, that may help to increase the cache capacity per se.
Yes, that's
Yes.
so. In other words, if you can take Parquet and you can filter it and reduce the amount of data you're caching, that would be actually really valuable.
So think
Right.
about it this way. If I know ahead of time that I will need only the 2 columns from that parquet,
yeah,
and if I will reformat that parquet on the fly to you to consist only the 2 columns, parquet self-described, it has schema, it has everything else, and I will deliver to the cache a small parquet.
so
Because I know upfront that that's
so
what is
Peter,
actually needed.
So Peter, I think that you're absolutely right, but there's 2 aspects to this, right? One of them is that if the bandwidth to that underlying data lake is limited, right, then and the compute near it is slow, right, it may not be worth doing that reduction there. It may actually be worthwhile pulling the data over to the cache and actually then reducing the data and doing exactly what you just said, but in our scenario, because that's a performant node, and it might actually, it just depends where to do that, right? But I'm not disagreeing. What you're saying is absolutely right.
There's also cheap and expensive transformations, and especially if there's something that can be done by, now, I mean, the compression in Parquet is an issue here. If it was self-describing and not compressed, in fact, this intermediate layer we're talking about could retrieve just the data that was necessary. You know, but it does make sense that, you know, there are some reductions which you could push down to weak nodes, and other reductions which you know, and in fact in our setup with Ceph, those could even be pushed down to there's a new structure for data operators at the OSD level that get pushed, you know, they can be pushed down to the actual, you know, storage nodes themselves. But, you know, but there's other operators where, you know, where being able to implement them efficiently at the level of nodes holding disks would essentially increase the cost of putting a disk in the system.
All right. I think that's a good discussion. I also see that we're running out of time. So thanks everyone for joining and for providing your feedback. We appreciate that. So we'll see you guys soon.
Yeah, nice work.
Yeah, no, this is great.
All right. Thank you, everyone. Bye.
Thank you.